now we have some progress. Okay. All right. So I'm going to talk about additive prime number theory. This is the theory of additive patterns in the prime numbers. So you all know what prime numbers are. Okay. Okay. So prime numbers 2, 3, 5, 7 neutral prime numbers. And by additive patterns, I mean patterns of numbers that can be described as linear combinations of parameters. So, for example, the twin prime conjecture contains the pattern of a twin, p equals 2. If you're interested in arithmetic regression, then the additive pattern is a equals r up to a plus k minus 1r if you want a progression from length k. And if you're interested, say, in the smallest prime gap, then you're interested in gaps between consecutive prime numbers. Okay, so there's been additive prime number theory is one of the oldest subjects in mathematics. You know, even the ancient Greeks had considered some questions concerning these problems, and there's still a lot that we don't know about the subject. So, for example, one of the oldest conjectures in the subject is the twin prime conjecture. That it's conjectured that there are infinitely many patterns p plus 2 that are both prime, infinitely many twin primes. But we still can't prove that, although we've come close. But we can do some other things. And I want to talk about some other patterns that we can now understand, in particular arithmetic progressions. Okay, so I'll first start with a result of myself and Ben Green from a few years ago, which is the following: that we don't know that the primes contain twins, or infinitely many twins, but we do know some other things. So, for instance, we do know that the primes contain arbitrarily long arithmetic regressions. So, in other words, given any k, there is an arithmetic progression of primes of length k. So 3, 5, and 7, for example, is a progression of primes of length 3. But you can do that for any length. Okay, so this is our result, but there was some previous work. So all the way back in 1929, van der Kolk established that there were infinitely many progressions of primes of length 3. So you can find many patterns A equals R equals 2R in the primes. That's what's called the Hardy-Littlewood circle method. Progress was stuck there for quite a long time. This is a fairly old problem, but progress was stuck for a long time. Length 3 is actually quite a significant barrier. Maybe I'll say why later. Okay, so after that, the only progress directly on the problem was by Heath Brown, who, roughly speaking, showed that there were infinitely many progressions of primes of length 3.5. What that means is that he found infinitely many progressions of length 4, where 3 of the elements of the progression, say the first 3, are prime, and the fourth guy is what's called an almost prime. It's either a prime or a product of 2 primes. Okay, so a prime is a number with no smaller factors other than 1 itself, and almost prime is a number with very few factors. So that's we sometimes call it a 3.5 result. Okay, so but progress was stuck there for quite a while because some new ingredients were needed. And so I want to talk about how the full theorem was finally proved. And it involves 3 basic ingredients that are combined, and I'll go through them one by one. So you have to first understand random models for the primes, Sieve theory, and something called Zimmer-Eddy's theorem. Okay. So we'll start with random models for the primes. Okay, so the funny thing about the subject, number theory, especially prime number theory, is that we can prove, I mean, the set of things we can prove is really quite small. I mean, it's been getting bigger over time, but still really quite small. But the set of things that we can conjecture is quite big. And we're actually much better at making conjectures in the subject than we are at proving them. To the extent that given almost any question about what the primes do, we have a conjecture that says what they do, and we believe those, and all the conjectures that we have, we believe quite strongly. There's a lot of numerical evidence, a lot of heuristic evidence. We just can't prove them, and that's really annoying. But it's just an aspect of the subject. So, for example, the twin prime conjecture that there's infinitely many twin primes, everyone believes is true, and I'll try to explain why in the next few slides, but we can't prove it. So it's because we have some very good heuristics as to how the primes behave. And roughly speaking, we believe the primes behave very randomly, and we can quantify that in a certain way. Okay, so Okay, so to explain this, so the starting point is one of the most important theorems about the prime numbers that we know, which is the prime number theorem. And the prime number theorem, which was proven about 100 years ago, says that if you want to count the number of primes up to n, so you pick a large number n, say 1 trillion, means how many primes are there up to n? The number of primes up to n is roughly n on log n. In the sense that the number of primes up to n, when you divide by n, when you divide by n over log n, the ratio tends to 1. So this is the prime number theorem. You can think of this as a probabilistic statement. In other words, if you pick a large number n, and then you pick a number at random, an integer at random between 1 and n, then a random integer between 1 and n has about a 1 in log n chance of being prime. So a random number between 1 and 1 trillion, if you pick one at random, has a probability 1 over log of 1 trillion roughly of being prime. That's a probabilistic way of thinking about the prime number theorem. Okay, so about 50 years ago, Kramer then proposed the following random model of the primes. So the primes are not a random set. There's only one set of primes in the world. You don't roll any dice, so you don't flip any coins to create the primes. But because when you actually plot the primes, it looks so random, Kramer proposed that you can model the primes by a random set. So the technical term for this now is that you think of the primes as a pseudo-random set, because they behave as if they're random. So I told you that if you pick a number n at random, the probability that it's prime is 1 over log n. So what you can do is that if you pretend that each integer n has an independent probability of 1 over log n of being prime, then if you make that random model, then that will give you a prediction for things like the twin prime conjecture and other conjectures like this. And Kramer's random model asserts that this prediction given by this random model is accurate, that the statistics for the actual primes should match the statistics for the random model. So even though the primes are not random, they should have the same statistics in the limit as n goes to infinity as a random model. This is the philosophy behind this random model. If you do this naively, you make every integer independent, have an independent chance of being prime. This turns out to not be completely accurate. I'll explain why. But you can fix it, and to give a model which we believe to be accurate. And if it is accurate, we could solve almost anything we want to do about the primes. But we just can't prove that this model is accurate, but we believe it is. So that's some generalities. Let me illustrate this with a concrete example. So let's talk about the twin prime conjecture. So, okay, so as I said, the twin prime conjecture we haven't solved yet. This is the conjecture that there's infinitely many pairs of p plus 2 of primes that just is 2 apart. Okay? So let me try to convince you why this conjecture really should be true. Okay, so let's give a fake proof of the twin prime conjecture. Okay, so let's pick a large number n, 1 trillion, you prefer a large number. And then, pick a large number big N, and then let little n be a number integer chosen at random between 1 and your chosen big number. So you pick 1 trillion and you pick a number little n randomly between 1 and 1 trillion. So this is a random number in this range. And the prime number theorem tells you that the number you chose, little n, has about a 1 in log n chance of being prime, because it's a random number from 1 to n. And if you add 2 to it, n plus 2 is also roughly a random number from 1 to n. Okay? It's a random number from 3 to n plus 2, but when n is big, it's almost the same range. So the prime number theorem also tells you that n plus 2 also has a probability of about 1 over log n, much of the lower order terms of being prime. Okay, so n and n plus 2 both have this probability of being prime. Now, if you assume that the events that n is prime and n plus 2 are prime are independent, if they're independent, then the probability that they're both true is the product of the probabilities that they're individually true. And then so then we conclude that the probability that n and n plus 2 are simultaneously prime should be about 1 over log squared n, the product of the two probabilities. Now, if you believe that, then and all that's saying, if you just unpack what this means, this is just saying that the number of twin prime between 1 and n is about n over log squared n. Okay? And as n goes to infinity, n over log squared n goes to infinity. So there are infinitely many twin primes, and we've proven the twin prime conjecture. Now, this argument doesn't work. You can see it, well, you can see it, well, there's many ways to see it doesn't work, but maybe the most obvious is that the same argument would also tell you that there's infinitely many consecutive primes, n plus 1, that are prime, and there aren't. Okay, only 2 and 3 are the only consecutive primes in the world. So there's something wrong with our argument. And of course, you should see what the problem is. The problem is independence. Independence is not true. Okay, so for example, the event that n is prime and n plus 1 are prime are highly dependent on each other. Okay, if n is prime, that makes it very, very hard n plus 1 to be prime. Okay, but so you could give up there, but or you can keep going. So okay, so what is the problem here? Okay, why is the answer wrong here? And the answer is wrong because of parity. See, our original random model is too naive. We're saying that the primes are distributed like a random set, but they're not distributed completely randomly because of parity. Primes are much more likely to live on the odd numbers than they are to live on the even numbers. Okay? So you can correct the model to take account for that. So our previous model was that every number got a 1 in log n chance of being prime. And that's not true because the even numbers really don't have that much of a chance of being prime. So you can fix the model by taking a fancier model. And so the fancier model would be to give the odd integers, well, okay, first of all, to give the even integers basically a 0 chance of being prime. Okay, so okay, I mean, it's not quite 0 because 2 is prime, but as n goes to infinity, it's so rare that you may as well just make it 0. So you give the even integers a 0 chance of being prime, and then to balance it, you give the odd integers a 2 in log n chance rather than a 1 in log n chance of being prime to keep the number density. So if you make this random model, so you now believe that even numbers have no chance of being prime, any odd number has a 2 in log n chance of being prime, and subject to parity, your events are independent. So the precise, okay, or more precisely, you have conditional independence of events relative to the parity. Then okay, well then first of all, then there are no more consecutive primes, n plus 1, okay, because if n plus 1, one of them is going to be even, and then so you have basically no chance of being prime. And then if you instead look at what happens with twin primes, n plus 2. So if you pick n at random, n is either even or odd. If it's even, then there's no chance of being prime. That happens half the time. The other half of the time, n is odd, and has a 2 in log n chance of being prime. N plus 2 is also odd, and has a 2 in log n chance of being prime. If you assume that those two events are independent, conditioning on them being odd, if they're conditionally independent, then they have a 4 log n chance of being prime half the time and 0 half the time. So you put them all together. What you get now with this corrected model is that instead of getting n over log squared n twin primes, which was the prediction from our incorrect model, this new model now predicts 2n over log squared n. Okay, so we have changed them up, we have fixed the model, and we get a new prediction. And so now maybe we prove the twin prime conjecture. Okay, there we have it. This model also is incorrect because there's more to primes than just being odd. Okay, so for example, this parity model would also tell you that there's infinitely many primes in the form n plus 2, n plus 4. But there aren't, because there's 3, 5, and 7. But other than that, n plus 2, n plus 4, one of them is always divisible by 3. So there are no other primes. Okay, because so the thing is that parity is not the only thing that controls the primes, also with divisibility by 3. Okay, so, but you can say, oh, let me also take into account divisibility by 3 into my random model. So now what you can do is that you can have an even smarter model, a better model, where, so we've already excluded the even numbers from being prime. Now we also exclude the multiples of 3 from being prime. So the only numbers that now have a chance of being prime are those that are co-prime with both 2 and 3. And to balance it, then on all the other residue classes, I guess 1 mod 6 and 5 mod 6, and that, you raise their probability being prime from 2 log n to so it turns out 3 log n in this case. And then you run the twin prime computation again, and this new model gives you a new answer. So instead of 2 n over log squared n, now you get as it moves. Now what you get is actually 1.5 n over log squared n. Now this is not the correct answer either because we haven't talked about mod 5. Okay, so then you put mod 5 in, and I'm not going to keep doing this, but you do it and then change the thing to 1.4 n over log squared n. So every time every time you take a piece of information about the prime, so primes are odd, primes are co-prime to 3, with one exception, primes are co-prime to 5, you can use each piece of information to update your random model to give a better model which you believe is more accurate. And every time you do that, you get a new model that gives you a new prediction for various statistics, like how many twin primes there are. And so you can keep doing this. You make more fancy and fancy models using models of 3, models of 5, taking those out. And you get various predictions, 1.5, interval log squared 1.4, and so on and so forth. And you can compute quite easily what the predictions would be. And what you soon discover is that these predictions, I mean, they keep changing, but as you put in more and more information, the predictions converge to a limit. That, after a point, I mean, taking out all the even numbers was a very big change. It doubled the number of twin primes. Taking out multiples of 3 was a reasonably big change, but not quite as big as before. Then taking out multiples of 5, it makes less and less of a difference. And after taking out multiples of 103, it does almost nothing. And so you have all these predictions, each of which is incorrect, but they seem to be sort of less incorrect as time goes by. And these predictions converge to a limit, and you can compute the limit very easily. It turns out the limit turns out to be not just some other constant times n of the log squared. And the constant is what's called the twin prime constant. It's 2 times a product over primes of something. It's a number that turns out to be about 1.32. So we have all these models, and their predictions asymptotically converge to this number, to this final answer. So the twin prime, the asymptotic model predicts that the number of twin primes at the end should be roughly this number times n over log squared n, which still goes to infinity, and still so that should still give you the twin prime prediction.
Do you prime constant in transcendental or algebraic?
It's almost certainly transcendental. We don't. It's very hard to prove any transcendental actually, but yeah, there's no reason to believe that it has any special properties other than, I mean, it's just this number. That's all it is. Okay. All right. So this final limiting prediction, 1.32 times n over log squared n. We believe this to be the true count for the asymptotic count for how many twin primes there are less than n. And you can do numerics. You can count how many twin primes there are up to say 1 trillion. And this asymptotic agrees to 4 or 5 decimal places. It's pretty good. In fact, and even the fluctuation looks like the square root of n, which is what it should be. But anyway, so we believe this to be correct. And more generally, there's a similar heuristic for other patterns in the primes. You can do the same thing not just for twins, but anytime you're counting whatever arithmetic progressions, or you're trying to write a numbers that sum of 2 primes or 3 primes, or you can solve anything like this. You can run the same sort of analysis. You take a random model, you keep updating it. Each random model gives you an answer. As you keep updating the model, the answers converge to a limit. You then believe the limit is the answer. So you have sort of an asymptotic limit of random models is the asymptotic limit. So none of the models themselves completely model primes, but the limit is believed to be an accurate model for the primes. And there's a formal statement for this, which is a bit technical, which I won't state here. It's called the Heidegger prime-tuple conjecture. Okay, and yeah, it's the way you should think about it is that it's saying that these sort of adjusted Payload models converge to something which is accurate for modeling the primes. Now, if we could prove this conjecture, we could do many things. Proving the twin prime conjecture is one thing, but we could answer many questions about the primes if we could prove this, but we can't. So the way I like to think about this is that we're modeling the primes just like we model a physical system. If you're a scientist, you have some mysterious physical phenomenon that you try to understand. So you use some experiments. Suppose you saw the primes for the first time and you didn't know that they were primes. They're just this funny set. So you start computing with them. So the first thing you guess is that this set is distributed randomly. But at some point, someone notices that all these numbers you're getting are odd, and so saying, okay, that's not a good. So that's not that. So our first hypothesis was incorrect. So you update your scientific model of what the set is. That this is a random subset of the odd numbers. But that's not quite correct either. Someone else discovers that you're just this mod 3 phenomenon and so forth. So you keep discovering all this structure in the primes. The primes avoid odd numbers, avoid multiples of 3, and every time you do that, you update your model. Okay, but when do you stop? Okay, I mean, at what point do you say, okay, I have learned everything I need to know about this set, and there's no other special structure that the set has, which is important. And we don't know when to stop. This is the problem. I mean, it could be that the primes, for example, happen to like the number 7 in the decimal expansion. That primes have more 7s in the decimal expansion than normal primes. This is not really the case. Well, we don't believe it's the case. But it could be. It could be that there's some sort of secret pattern or secret, I don't know, like a conspiracy, if you like, in the prime numbers. That they have some extra law of nature that we haven't discovered yet. And if they did, then our current models for the primes, our random models of primes, would probably be wrong. We'd have to update that to deal with some extra fact about the prime numbers that we don't know yet. But okay, so we don't know how to exclude that possibility. We don't know how to show that. We don't know how to stop, someone clever in the future discovering a new pattern in the primes that we haven't really seen. And that's the real problem with the subject. We just don't know how to stop unexpected patterns from happening. Okay, we believe that the structures that we've seen, so primes that are odd, cofactor 3, cofactor 5, these are the obvious patterns in the primes, and there should be no other patterns in the primes of any significance. No other patterns that are big, that are strong enough to change the number, to change things like the number of twin primes up to n. Okay. For the purposes of doing statistics, the obvious patterns should be the only patterns, but we can't prove that. I think I've actually said a lot of this already. Yeah, okay. So, I mean, one can imagine, for instance, the primes have some sort of conspiracy that every time a prime decides to live at n, the next prime is supposed to move a little bit distance away from n, right? And maybe they just agree to do this after a certain point, beyond what we can see of computers. That should not happen. Okay, I mean, there should be no. I mean, the primes don't have this sort of level of intelligence. Okay, but it could potentially happen. Okay, and it could be a conspiracy, if you like. And the thing about conspiracies is that it's very hard to disprove conspiracy. I mean, you can always just sort of cover up conspiracies with a bigger conspiracy or something. Okay, so this is the limitation of the random model. So I mean, everyone believes they're correct, but we can't prove it. Okay. All right. Okay, so let's turn now to what we can prove. So let's leave random models aside for the time being. Okay, so there's another way to think about primes, which is Sieve theory, which is something you learn in primary school even. And it's a very simple way to create primes. And it's one which is, I mean, it's very elementary but remarkably effective. But it doesn't quite solve the problem for a certain key reason. So if you want to find primes, then you can do it by various sieves. And the simplest sieve is called the sieve of which you should have learned in primary school or high school. So if you want to find all the primes in a certain range, let's say from n over 2 to n, where n is a big number, you can do it by starting with all the numbers from n over n to n, and then you get rid of some of them. So you cross out all the even numbers, all the multiples of 2, you get rid of them, you sieve them out. And then you cross out the multiples of 3, multiples of 5, 7, and so forth, up to the multiples of root n. Okay? And once you get rid of all those multiples, then you what's left is just the primes. Okay, so that's one way to create primes, and it's not hard to modify the sieve to also sieve out just twin primes. So suppose you wanted to count all the twin primes from n over 2 to n. Well, you throw out all the even numbers because even numbers can't be twins, be primes, let alone twin primes. And then you throw out multiple of 3, but you also throw out multiple of 3 minus 2, because those numbers when you add 2 would not be prime. Let's just work with big numbers. Big numbers bigger than n over 2, so you don't have to worry about the small primes. And so rather than remove one residue class for every prime p up to root n, you remove 2 residue classes. And that would be a sieve that counts twin primes. And so what you can hope to do is just keep track of how many numbers at every stage, how many numbers are still left in this sieve. So, to begin with, so for example, to begin with, if you count twins n plus 2 in the entire range, in this interval n plus 2 to n, then it's very easy to count how many pairs there are in the whole integers, not primes, but integers. That's by n over 2 plus big O of 1. Big O of 1 because of round-off error, because you have to take fractional parts of n over 2 and so forth. Okay, so that's how many twins there are in the entire integers. If you take out all the multiples of 2, then there are fewer twins now, turns out to be n over 4. Then if you take out all the multiples of 3, then it's n over 12, and so on and so forth. And you can keep taking out all these multiples, and if you can do this root n times, then at the end of the day, you have just the twin primes from in this range, and if your bound here is still positive, then you've shown there's at least one twin prime in between n, and then n is arbitrary, that gives you infinite twin primes. So this has been a dream for 100 years to do stuff like this. There's a big problem though, it's because of the stupid little O1 error here. Okay, so to begin with, initially little O1 is tiny compared to n over 2. But if you do this naively, and naively means using the inclusion-exclusion principle, every time you sieve out something new, this big O1 error is twice as big as it was before. It grows exponentially. Whereas the main term is shrinking. And what happens because of this is that if you do this naively, after about log n steps, the error term is now bigger than the main term. And so the lower bound is worse than the trivial lower bound of 0. And so you acquire no information after about log n steps. Okay, and you need to get a root n. Now, you can be smarter than this. So the sieve of Eratosthenes was the first sieve. I mean, it's a 2,000-year-old sieve. But there are smarter sieves out there which have a better, I mean, they're more complicated, but what they do is that they make the error term smaller. So the problem is that the inclusion-exclusion principle just has too many terms in it. That's the problem. So you can smooth out the inclusion-exclusion principle by adding by doing this adding and subtracting a little bit more carefully. So rather than sort of crossing out numbers which are multiplied and so forth, what you should do is that you should actually give every number a score, and you should lower the score whenever you're divisible by something, and raise it if you're not divisible by something, but do it in some sort of smooth manner. And they're very complicated sieves, and there's been 100 years of progress in sieve theory to understand what's the best way to adjust these weights to get really good control of these error terms. And so because of this, people don't need to suffer log n anymore. They can push the level at which they can control the sieve up from log n to much higher. But they can't reach root n. Even the best sieves, and we now have formal proofs that there are limits to sieve theory. Even the best sieves, they cannot get all the way up to root n. They stop at around a smaller power n, like in 1/4 and 1/5. It's very common. But there is an inherent limit to the power of sieve theory. And this is now well understood. There's something called the parity problem. The parity problem is basically the statement that sieve theory cannot tell apart primes, which are from semi-primes. Semi-primes are numbers which are products of two primes. Or more generally, primes of an even number of factors and primes of odd number of factors are very, very hard to tell apart by sieve theory. And it's because of this, you can't ever hope to get rid of the semi-primes. You always have to carry them along. And so any result which is written just by sieve theory never gets to count primes directly. It always counts primes and also semi-primes as well. They always come along to the right. And this is related to the fact that the sieves stop at around 1/4. You really can't go any further. So that's a very annoying problem. But it does get you somewhere. So sieve theory, okay, so there's 100 years of progress in sieve theory. If you want to summarize it in a single sentence, sieve theory can control sieves up to a height such as say in 1/10, okay, rather than and 1/2 is what you want, but you can get up to something like in 1/10. And even if you put everything to the limit, maybe into 1/4, if you're really careful. Okay, so your sieve stops at some point before it's complete, and so you don't just get the primes anymore. So the sets that sieve theory can count are not the primes, but sets that are bigger than the primes. The sets of what are called almost primes. Numbers, so products of a small number of large primes. So see, if you throw out all the multiples of numbers less than 1/10, what's left? The numbers that are left can only be divisible by primes bigger than 1/10, and they can only be 10 primes, even 9 primes actually, that divide n at that point. The only numbers that are left are what are called almost primes, numbers with very, very few prime factors. Okay. And so what sieve theory has done for us is that, I mean, sieve theory was designed to count primes. This is why sieve theory was invented. And it has never worked. It's been very frustrating that sieve theory has never been able to count primes directly. Well, very, very few exceptions, but in general, you cannot count primes from sieve theory. But what sieve theory can do, and it does extremely well, is that it counts almost primes. That if you want to count, for example, how many twin almost primes there are from 1 to n, sieve theory does this for you. It gives you the right asymptotic. It gives you everything. It gives you everything you want. Okay, not quite everything you want, but it gives you a lot of what you want. Okay, much a lot of technical issues. And what Sieve theory teaches us is that this Heidegger prime-two-cause conjecture, which is that these random models for the primes are supposed to be asymptotically accurate. We can't prove those for the primes, but Sieve theory lets you prove the analog of those random models for the almost primes. We know that those are accurate. So if you want to count twin almost primes, if you want to count arithmetic progressions of almost primes, things like that, the random models give you a prediction, and Sieve theory tells you the prediction is correct. Okay, so this we do know. So we can rigorously justify all our conjectures if you're willing to talk about almost primes rather than primes. Okay. But unfortunately, all the big problems we care about, they don't have the word almost in them. Okay, the problems that we care about the primes have, we want the primes themselves. So, I mean, on the one hand, Sieve theory is very satisfactory. On the other hand, it's very unsatisfactory. Oh yeah, okay. But the one important thing I wanted to say is that, okay, almost primes are, of course, there's more almost primes in the world than primes, because primes are a subset of the almost primes. But there's not many more. It turns out, so the prime number theorem tells you that the number of primes in the world is n over log n. The number of almost primes in the world is a constant times n over log n. You can compute. It's actually one of the first things you do in Sieve theory. And C depends on what you mean by almost prime. So if almost prime is, let's say, numbers of 10 prime factors, which are bigger than 10 to 1/10, the C is roughly 10 or 10 over E or something like that. If you define it almost primes differently, you get a different C. But the point is that the almost primes are only a constant factor bigger than the primes. Or, put another way, the primes are a positive density subset of the almost primes.
Or the C is independent of n.
C is independent of n. Yeah, that's very important. But it does depend on what you mean by almost prime. Okay, so does almost prime mean you have 2 factors or 3 factors or 4 factors? There's parameters which I don't want to show. Okay, because that's okay. So one thing I'm not thinking about Sieve theory is that if you actually look at any paper in Sieve theory, it's very messy. There's lots of little parameters and epsilons and things, and I just don't want to show you that. Okay.
So this density is uniform, and then
yes, yeah, the tensor limit. Yeah. So the number of primes divided by the number of almost primes from n to 2n converges to a limit, as long as you keep the definition of almost prime fixed. Okay. This is a theorem proven in 1975. Coincidentally, it was the year I was born. Okay, so it's Zemurati's theorem. So it's about arithmetic progression. So it says take any set of integers A, any set of integers, but the only thing you require is that the set is big. And what big means is that it has positive upper density. And what positive upper density means is the following. For any large number n, you look at the density of A in the interval from -n to n. So you count how many points there are in the interval from -n to n in A, divide that by the total number of points in -n to n, which is 2n plus 1. Take the limit, actually limit them soup, but never mind. Take the limit of that. If that's positive, we say we have positive upper density. We have infinitely positive lower density. So take 1% of the integers, if you wish. Okay. Then any set which is that big, any set of integers which is that big, will contain lots and lots of arithmetic progressions. And in particular, it contains arbitrary long progressions. Given any k, inside the set you can find the progression of k. In fact, you'll be able to find infinitely many. So this is an amazing theorem. I mean, it may seem, okay, it's just a theorem. It doesn't look so just like any other theorem when you first look at it. But this is saying something very special about arithmetic progressions. That arithmetic progressions are, in some sense, indestructible. That you can't get rid of them just by moving your set around, unless you destroy almost all your set. You have to basically, reduce your set to nothing, which is a set of zero density, if you want to remove all the progressions.
What is the main idea of the proof?
I will next slide.
Oh.
Okay, but okay, I'll start with that. So before I do so, let me just point out that if you replace progressions by any other pattern, or not by any other pattern, there's a few other patterns with a similar theorem, but for most patterns, this theorem is false. For example, twins, n plus 2. Okay, some sets contain twins and some sets do not contain twins. But it's very easy to find very big sets with no twins, such as the multiples of 3. Multiples of 3 are density 1/3. It's a huge set, but no twins. It's very easy to get rid of twins by just arranging your set in the right way. But you can't get rid of progressions this way. Okay, for example, multiples of 3 have plenty of arithmetic progressions. And you know, if you think about it, it's really quite hard to find a big set without progressions, and it's very simple as it is in fact impossible. Yeah, so this is an amazing theorem. It has amazing proofs. In fact, there are about 5 proofs, at least, of this theorem. And each proof has been incredibly hard, incredibly, but also incredibly influential. I mean, it's not a stretch to say that each of these proofs has spawned an entire proof mathematics. Except maybe the last one, which is something that's very new. But you know, so the original proof of similarity was this amazing combinatorial proof, just an immense induction argument, like 7, 8 epsilons flying around. We just recently won a prize for this paper, actually. Much more recent one, and then 2 years afterwards, Hilda Furstenberg gave what looked like a completely different proof, which we now actually understand is related, but using something out of left field. He used the language of ergodic theory. He found a way to take a limit, which converted this combinatorial problem about finding progressions in the integers to a problem about recurrence in analytical systems. And then he proved that theorem about recurrence using techniques from ergodic theory. It's an amazing paper, and again, that spawned, as many papers spawned, you know, I mean, the entire computer science devoted to generalizing actually just one lemma in the original paper, the similarity regularity lemma. And yes, the whole field of mathematics devoted to Furstenberg recurrence theory. In 2001, Tim Gowers gave a third proof of this theorem using a generalization of Fourier analysis, quadratic. So Fourier analysis you can think of as the study of how functions correlate with linear phases, e to the I, c times x, kind of thing. You can talk about generalized Fourier analysis, where instead of taking linear phases, you take the quadratic phases, e to the I c x squared, e to the I c x cubed, things like that. And then there's a whole theory of that, which didn't exist until Tim Gowers invented it, okay, and it's still being invented right now. And that gave a third proof of this theorem. There was a Fourier effort a few years afterwards to prove, there was a fourth proof using something called hypergraph theory, which I won't talk about here. And then very finally actually, so Paul Pornkeys, and as Paul mentioned this, that we'll be working on these massively collaborative projects, polymath projects. And the very first one, this project, was to prove actually a different theorem, but that theorem implied generally similar as a corollary. So, and it succeeded, and we actually got a fifth proof, which is actually the most elementary of all the proofs of this theorem. Okay, so there are many difficult proofs. We sort of know that the proof of this theorem has to be difficult, that we're not going to find a 3-line proof of this theorem. And the reason is that all large sets have progressions, but there's at least 2 different ways in which they can create progressions, and those 2 ways are very, very different, and you have to accommodate both of them. See, the thing is, we don't know anything about our set. We have this large set of integers, but other than being large, it could be almost anything. And in particular, it could be either very, very structured or very, very random or something in between. So at one extreme, your set A could be extremely structured. So what I mean structured, for example, take the even numbers. Okay, very periodic. Okay, if you have a very rigid periodic structure, that's one type of large set. Okay, and so a very rigid periodic structure, like the multiples of 3, can't have, for example, any twins. But it does have lots of progressions. It's clear that something which is very periodic clearly has a lot of progressions in it because of the structure. At the other extreme, you could take a set that's very random. Take, for example, flip a coin for each number. If it's heads, put it in your set A. If it's tails, put it out. You get a random set. Random sets also have lots of progressions, because any given progression, say progression of length 3, would have a 1 in 8 chance of lying in your random set, because each of the 3 guys has an independent chance of 1/2 lying in your set. I told you about these random models that don't work for the primes, but if you're actually working with a random set, they actually work. So if you have a random set, then every progression has a 1 in 8 chance of being in your set. There are infinitely many progressions, and so it's very easy to then see that with probability 1, you're going to have an infinite number of progressions of any length. So both in the random case and in the structured case, you have lots of progression. You can also consider hybrid sets, where you take, say, a structured set, let's say the even numbers, and then you take just half of them. So you at random, you take for every even number you flip a coin, if it's heads you put it in A, tails you put it out. So it's a random subset of a structured set. So those sets, the mixtures of structured and random sets, they also contain lots of progressions, because the even numbers already contain lots of progressions, and then when you pass to a random subset, a large fraction of those progressions survive and are still inside your random subset. So in all of these sets, structured sets, random sets, and then random subsets of structured sets, every such set has progressions. And all of these 5 proofs that I just listed, they all have the feature that at some point in the argument, I mean, they all use different language, and it's all arranged differently, but each of the proofs at some point divides into cases. That your object, so your set, in the ergodic theory proof, it becomes a dynamical system, and the graph theory proof becomes a graph, but never mind. Your object is either very structured, very random, or some combination of the two. And you have to have some decomposition like that. Because otherwise you can't prove the theorem, because the way you get progressions from the two cases are just so different that there should be no way, no one expects there's a way to do it in one go. So you have to somehow split up the structure in random parts. And that's why all the proofs are hard. Okay, but it's also why the theorem is useful. Okay. All right, so let's put it all together. So where are we now? Okay. So I've shown you Zemurati's theorem, which says that any set of positive density, any large set, has got lots and lots of progressions. Now, we wanted to prove that the primes contain arbitrary long progression. Now, unfortunately, the primes do not have positive density. Okay. If it did, we would be done since Zemurati's theorem was proven. Okay, the prime number theorem, in fact, tells you the density of the primes is 1 over log n. It goes to 0. The primes have 0 density. So the primes have 0 density in the integers. But on the other hand, the primes have positive relative density relative to the almost primes. So while they're very small, sparse in the integers, they are dense in the almost primes. And the almost primes we understand very well. We have all the Sieve theory. The almost primes, so they behave quite well. So for example, they have all the progressions that we expect them to do. Right? It's very easy to show that the almost primes contain lots of progressions. So all you do is put all these things together. And okay, so you put these 3 facts together and you get this theorem. All right, so how does that work? So, all right, the actual proof is the refutation I'm not going to talk about, but this is the informal idea. Okay, so I told you that the primes are we have this random model for the primes, this sort of asymptotic Kramer random model. Now, if that model was correct, then we'd be done. Okay? If the Kramer model was accurate, then you just apply it, and it will give you the prediction for how many progression of primes there are, and it's a positive number, so you get a lot of abstract progressions. Okay, but we don't know that the random model works. It could be that there's some extra structure, that the primes are doing something else that we don't know about. Okay, as I said, maybe the primes favor the number 7. The primes are larger on the set of numbers whose last digit is 7, and not large outside, and less large out of them. But as we saw, every time you have some new structure like that, you can always put it into your model, change the model, and get a new model which is presumably better. So you can just do that. Okay, every time, okay, so you take a model for the primes, either it gives you the right count for the progressions, or it doesn't. If it doesn't, that's because the primes have some extra structure. You identify that structure, you use it to change the model, you update the model, and that gives you a more complicated model. And then you ask, does this guy model the primes? And if it does, stop, otherwise you adjust it again. And so you repeatedly adjust this model. And it turns out, and this is hard to show, but this sequence of adjustments stops in finite time. That there's a certain energy quantity which keeps increasing every time you move more complicated, but on the other hand you can show it's bounded. And because of that, it has to stop at some point. And at some point, you stop and you get some funny model for the primes, throwing in all this unusual structure that you detected. And that will keep, and somewhere out there is some crazy model for the primes which actually works. Okay. This you can show just by abstract nonsense. But okay, but if that's all you knew, then that's useless because you're modeling the primes by some crazy object that you just don't understand at all. Because you're throwing in all this weird structure for primes that it's conjecture they don't even exist. But you throw in some weird, funny version of the of the Kramer random model that you can't compute with. But we do know that whatever this crazy random model of the primes is, see, we know that the almost primes, which is just a bit bigger, are modeled by a really nice random model, basically by a very uniformly distributed random model. And the primes are a constant factor smaller than this sort of uniformly distributed model. So this funny crazy random model of the primes can't be too crazy because it's somehow bounded from above by a constant, by a uniform model. And you can make that precise, but it's complicated, but you can do that. And what that shows, at the end of the day, what you can show is that this funny, crazy random model of the primes, it need not be completely uniformly distributed, but you can but it must look like a random. It must be sort of look like a completely random set on some dense subset of your Hoviniges. So in your Hoviniges, in the set of Hoviniges, there's some dense subset such that this funny model of the primes looks like just a random subset of a dense set. So in other words, the primes behave as if, at least on the dense set, they behave randomly on some dense set. Okay, but we have Generalized theorem that says that whenever you have a dense set of integers, you have lossless arithmetic progressions. And if you take a random subset of that dense set, that random subset will also have lossless of arithmetic progressions of integers because each progression has got a positive probability of surviving when you pass it to the dense set. And hence, your random model has a lot of progressions in it. But it also models the primes, and so hence the primes of those progressions. Okay, so that's how you put everything together. Okay, so so that's what you can do. Now, the last few minutes, I wanted to say, so this was stuff we did 5 years ago. What we've been working on since is generalizing all this stuff. Well, okay, two things. One is that this proof, this argument tells you that there's infinitely many progressions, but of primes, but it doesn't tell you. It's not completely satisfactory because it didn't provide the correct count. Well, I mean, the highly liberal conjecture also predicts how many progressions of primes there are up from 1 to n. This argument gives you a lower bound, ultimately because Generalized theorem gives you a lower bound, as it turns out. But it doesn't give you the right asymptotic. And the reason is because, I mean, from that argument that I just gave, it is possible that primes contain some sort of funny extra structure in them, which would change the number of progressions that they have, but it wouldn't send it to 0. Okay, so Generalized theorem allows to have a very funny number of progressions of primes, but it just can't be 0. But it can be something else. Okay, so we want so first of all we want the right asymptotic. We want to know exactly how many progressions of primes there are from 1 to n, or at least asymptotically. The other thing is that we're not just interested in progressions. We want to do other things. Ultimately, twins and so forth will be wonderful. We can't do that. But we also want to understand other patterns. But of course, when you do other patterns, I mean, what makes arithmetic progression so special is Generalized theorem. Well, in any other pattern, you don't have Generalized theorem. And so we wanted to know, can you get around, can you not use Generalized theorem and still get similar results? So you can consider more general patterns. Okay, this is just a bunch of words, but okay, I mean, in arithmetic progression, it's just a whole bunch of linear forms parameterized by two variables, n1 and n2. And you can consider more general patterns. You could ask for parallelograms or cubes, or you can ask for many other patterns. And for any pattern of this form, you can ask you can ask the same type of questions that we ask for progressions. And many problems in number theory are just in additive number theory are just the question of how can you count how many patterns of a certain type there are. So twin primes are counting this pattern here, n1 and n+2. The even go back conjecture asking whether a certain number can be written as symmetry of primes is basically counting solutions to how many times this pattern occurs in the primes. And the odd go back conjecture is how many times, which is considered writing numbers the sum of 3 primes, is how many times you can find this pattern inside of primes for some fixed large number n. And in terms of that, we can almost solve this conjecture. So, for example, Vinogradov many years ago showed that every large odd number, sufficiently large odd number, is a sum of 3 primes. We can count patterns like this, but we can't count patterns like this. And we now begin to understand why. Basically, any pattern that involves 2 or more parameters, we now have a method of counting. So arithmetic regressions are an example of a pattern of 2 parameters. And this pattern here, summing numbers, writing numbers as sum of 3 things, that's 2 patterns. Anything with 2 or more parameters, we have a chance of counting. And anything with 1 parameter, we don't have any chance, at least for code technology. So that's very annoying because I mean these are the 2 conjectures we most like to solve in the subject. But the things involving 2 or more parameters we now know some chance of doing. Okay, so let me. Not every pattern appears in the primes. So I told you that consecutive primes, n plus 1, appear very, very rarely. And that's because there was an obstruction mod 2, right? n plus 2, n plus 1, among n plus 1, one of them is always prime. One of them is always even. And so hence very rare prime. And so that's what we call an obstruction mod 2. And more generally, if you have a pattern where one of the guys always has to be divisible by p, then we call it an obstruction mod p. And then it's very hard for that pattern to give you primes. There's also what we call obstruction to infinity, because primes are not only co-primary to p, with one exception. They also tend to be positive. So if you have a pattern where one of the numbers is always negative, or maybe when you find many exceptions, then it's really hard for that pattern to live in the primes. And so if that happens, you say that you have no obstruction at infinity. So there are these 2 obvious things that stop patterns from lying in the prime. One is that primes are positive, and the other is that they're co-prime to small moduli. And there's this big conjecture, which is that those are the only 2 obstructions. That if you have any pattern which has no obstruction mod p and has no obstruction to infinity, then we should be able to find that pattern in the primes. Okay, the 2 obvious things that stop you from lying in the primes are the only things. That's called the generalized Hardy-Lederer prime tuples conjecture. If it's true, it implies twin prime Kurobat conjecture. It implies all kinds of things. In the last 3 or 4 years, Ben Green, Tomas Ziegler, and I have finally settled this conjecture if you have 2 or more parameters in your pattern. So the actual result is that it's a bit technical, but if you have a pattern which is a whole bunch of affine linear forms coming from various parameters, and you need a sort of independence condition that you're not allowed to have things like twins. So